December 19th is coming, and something extraordinary is about to happen that most people won't even realize until it's already passed. A visitor from another star system. Scientists believe this comet has journeyed through space beyond our solar system for a very long time, possibly millions of years, though the exact time span is still unknown, will reach its closest point to our planet. And despite everything NASA has told us, there are questions about this encounter that remain unanswered. This isn't science fiction. This is happening in less than a month, and the object in question, a comet designated 3I Atlas, carries with it mysteries that challenge everything we thought we understood about how our solar system interacts with the rest of the galaxy. What makes this moment different from every other cosmic event you've heard about this year is that this visitor will never return. Once it passes Earth on December 19th, it will continue its journey outward, leaving our solar system forever, and we will have missed our only chance to understand what it might have revealed about the universe beyond our sun's influence. The questions surrounding this encounter aren't the kind you'll find answered in standard news coverage. Everyone keeps talking about how this comet is safe, how it poses no threat, how it's just another astronomical event for scientists to catalogue and move on from. But what if what we've been told isn't the complete picture? What if the real story of December 19th isn't about danger at all, but about what we're about to witness that has never been witnessed before? NASA has been tracking this object with multiple spacecraft, observing it from Mars, from deep space missions, from solar observatories that weren't even designed to see something this faint. They've watched it disappear behind the sun and emerge changed. They've documented details about its structure and behaviour that don't fit the usual patterns. And yet, when you search for information about what will actually happen on December 19th, you find the same recycled statements about distance and safety, but very little about what makes this moment unprecedented. Here's what we know for certain. 3I Atlas originated from beyond our solar system, from the space between stars where no human instrument has ever travelled. It's only the third confirmed interstellar object ever detected passing through our cosmic neighbourhood, following Oumuamua in 2017 and Comet Borisov in 2019. Each of these visitors has rewritten parts of our understanding about what exists in the vast emptiness between star systems. But 3I Atlas is different. Its trajectory brings it closer to Earth than either of its predecessors during their respective flybys. On December 19th, it will reach a distance from our planet that, while still incredibly far by human standards, represents the nearest approach any confirmed interstellar comet has made to Earth in recorded history. This is not a drill. This is not a maybe. This is happening, and the date is fixed in the astronomical calendar with precision measured in minutes. The comet's journey through our solar system has been nothing short of dramatic. It swept past the Sun on October 29th, reaching its perihelion, the closest point in its orbit to our star, and during that passage something unexpected happened. Multiple NASA spacecraft captured images of this interstellar traveller at different stages of its approach and departure from the Sun. Mars orbiters photographed it from their vantage point in the inner solar system. Deep space missions like Psyche and Lucy, travelling to the asteroid belt and beyond, turned their cameras to document this visitor from another stellar neighbourhood. The Solar and Heliospheric Observatory, SOHO, which has spent decades watching the Sun, managed to capture 3I Atlas during its closest solar approach, despite predictions that it would be too faint to detect. And then came the disappearance. For weeks in late October and early November, 3I Atlas vanished from view, hidden behind the Sun from Earth's perspective in what astronomers call solar conjunction. During this time, no ground-based telescope could track it. No Earth-orbiting observatory could see it. The comet was effectively invisible to humanity, passing through the most dangerous region of the solar system, where temperatures soar and solar radiation tears apart anything too fragile to survive. When it finally emerged from this cosmic blind spot in mid-November, astronomers around the world turned their instruments toward the sky, searching for the interstellar visitor, wondering if it had survived its close encounter with our Sun. What they found raised more questions than it answered. The comet was still there, still intact, but its appearance had changed in ways that demanded explanation. Now, as December approaches, 3I Atlas is heading outward through the solar system, moving away from the Sun and simultaneously approaching Earth along a trajectory that has been calculated with remarkable precision. Astronomers know exactly where it will be on December 19th. They know the distance it will achieve from our planet, down to specifications that would have been impossible to predict just decades ago. They know its speed, its direction, its composition based on spectroscopic analysis of the light reflecting off its icy surface and the glow of gases in its coma and tail. They have more data about this object than any previous interstellar visitor, and yet there's a gap between what the data tells us will happen and what it means. The numbers are certain. The implications remain open to interpretation. This is where the story gets interesting. Because December 19th isn't just about a comet reaching a specific distance from Earth. It's about what happens during that moment of closest approach that we can observe, measure, and learn from before this object disappears into the interstellar darkness, forever. It's about questions that have been circulating in astronomy communities and online forums. Questions about whether this comet's behavior matches expectations, whether its trajectory has shown any anomalies, whether there's something about its composition or origin that current models can't fully explain. These aren't conspiracy theories. These are legitimate scientific inquiries emerging from observations that don't quite fit the comfortable narratives we've built around how interstellar objects should behave. Stay with me, because in the next minutes we're going to uncover what will actually happen on December 19th when this visitor from another star system makes its closest approach to Earth, separating the verified facts from the speculation, examining what NASA's fleet of spacecraft has really observed, and understanding why this moment matters more than most people realize. We're going to trace the comet's journey from its October perihelion through its solar conjunction disappearance to its current approach toward our planet. We're going to look at the specific observations that have raised questions in the scientific community. And we're going to explore what this encounter tells us about the nature of the galaxy we live in and our place within it. But before we go deeper, I need you to do something. If this cosmic mystery has grabbed your attention, if you're curious about what December 19 will bring, hit that like button right now. It tells me you're ready to explore the questions that don't have easy answers, and drop a comment telling me where you're watching from, because on December 19th, people all over this planet will be looking up at the same sky, searching for the same interstellar visitor, united by curiosity about what exists beyond our solar system. Let me know your location, because I want to see just how global this moment of cosmic connection really is. Your engagement doesn't just help this video reach more people who care about these questions. It creates a community of observers who refuse to accept surface-level answers when the universe offers us something extraordinary to witness. The clock is counting down. December 19th is not far away. What happens on that date will never happen again with this particular object. Once 3, I-Atlas passes Earth and continues outward. It will fade from view, moving beyond the reach of our telescopes, beyond the influence of our sun, back into the interstellar medium from which it came. This is our one chance to observe it, study it, and understand what it reveals about the cosmic neighborhood we inhabit. And the questions surrounding this encounter demand answers that go beyond simple assurances about safety and distance. They demand we look at what makes this moment unique, what makes it valuable, and what makes it something worth paying attention to in a world filled with distractions and competing claims on our attention. So let's begin this investigation properly. Let's trace the path that brought this interstellar visitor to December 19th. Let's examine the evidence that has accumulated from multiple spacecraft and observatories. Let's separate what we know from what we suspect. And let's understand why this close approach matters not just for astronomers with access to professional telescopes, but for anyone who has ever looked up at the night sky and wondered what else is out there, travelling through the darkness between the stars, occasionally passing through our small corner of the galaxy on journeys we can barely comprehend. The story of 3I Atlas and December 19th is bigger than one comet and one date. It's about how we're learning to see the universe in new ways, recognizing that our solar system isn't isolated but part of a dynamic galactic environment, where visitors from other star systems pass through regularly, mostly unnoticed, but sometimes, just sometimes, coming close enough for us to witness their passage and learn from what they reveal. Understanding what will happen on December 19th requires understanding the journey that brought 3I Atlas to that moment. This comet didn't just appear suddenly in our sky. Its path through the solar system has been traced backward through careful observation and orbital calculations, revealing a trajectory that confirms its interstellar origin beyond any doubt. Unlike comets that orbit the Sun in elliptical paths, returning predictably every few years or centuries, 3I Atlas follows what astronomers call a hyperbolic orbit. This means it's moving too fast to be captured by the Sun's gravity. It came from somewhere else, and it's going somewhere else, with our solar system being merely a brief waypoint in a journey that stretches across distances so vast they challenge comprehension. The comet entered the inner solar system from above the plane where most planets orbit, diving down toward the Sun at an angle that immediately marked it as unusual. Its velocity exceeded what would be possible for an object bound to our Sun's gravitational influence. The numbers told a clear story. This was not a resident of our cosmic neighbourhood. It was a traveller from beyond, carrying with it ices and dust that formed around a different star, in a different planetary system, under conditions we can only infer from the evidence we're able to gather during its brief passage through our observational range. Every measurement, every spectroscopic reading, every photograph added pieces to the puzzle of where this comet came from and what it might reveal about the environments that exist around other stars. As 3I Atlas approached the Sun through September and October, NASA's network of spacecraft across the solar system took notice. This wasn't planned. These missions weren't designed to observe interstellar comets, because until very recently, we didn't even know such objects passed through our solar system with any regularity. But space agencies have learned to be opportunistic. When something unusual appears, when a target of scientific interest enters the observable range of any spacecraft with functioning cameras and instruments, mission controllers reprogram, retarget, and capture what they can. This is how science adapts. This is how we maximize the return from expensive missions already in space, by being flexible enough to study unexpected opportunities when they arise. The Mars orbiters were among the first NASA spacecraft to capture clear images of 3I Atlas. From their position orbiting the red planet, they had a unique perspective on the comet's approach toward the inner solar system. The images they transmitted back to Earth showed a faint smudge with the characteristic tail that marks a comet actively releasing gases and dust as solar radiation heats its icy surface. These weren't close-up portraits. Mars and the comet were still separated by vast distances, but they were the closest views any NASA spacecraft would achieve of this interstellar visitor, and they provided valuable data about the comet's size, its level of activity, and the structure of its coma, the cloud of gas and dust surrounding its nucleus. At the same time, the Psyche mission, travelling outward toward the asteroid belt on its way to study a metal-rich asteroid, turned its instruments toward 3I Atlas. So did Lucy, another asteroid-focused mission on a complex trajectory that will eventually take it to study Trojan asteroids near Jupiter. Neither of these spacecraft was designed for comet observations. Neither had the comet in their mission plans when they launched, but both were in positions where they could contribute to the growing database of observations documenting this interstellar visitor's passage through our solar system. Each image, each data point added to the comprehensive picture astronomers were assembling, trying to understand everything they could about this object during its brief period of visibility. Then came October 29th, the date of perihelion when 3I Atlas reached its closest approach to the Sun. This was the critical moment in the comet's journey through the inner solar system. At perihelion, the intense heat and radiation from our star would test the comet's structural integrity. Many comets don't survive close solar approaches. They fragment, disintegrate, or undergo dramatic changes that alter their trajectories and their appearance. Would this interstellar visitor, formed around a different star and potentially composed of materials with different properties than solar system comets, survive the encounter? The answer would tell astronomers important things about the comet's composition and the conditions under which it formed. SOHO, the Solar and Heliospheric Observatory, positioned at a gravitationally stable point between Earth and the Sun, became the crucial instrument for observing 3I Atlas during perihelion. SOHO's LASCO coronagraph blocks out the Sun's overwhelming light, allowing it to observe the region immediately around our star where comets often appear during close approaches. For decades, SOHO has been one of the most prolific comet discoverers in history, capturing hundreds of small comets diving toward the Sun, most of which are destroyed in the attempt, but 3I Atlas wasn't expected to appear in SOHO's field of view. Predictions suggested it would be too faint, too distant from the Sun even at perihelion to register against the bright background of the solar corona. The predictions were wrong. SOHO captured 3I Atlas during its perihelion passage. The images showed the comet moving through the inner solar system, its tail streaming away from the Sun in the direction expected from solar radiation pressure. This was more than just a successful observation. It was confirmation that the comet had survived its closest solar approach intact. It hadn't fragmented. It hadn't disappeared. It was still there, still active, still releasing gas and dust as the Sun's heat vaporized ices from its surface. This survival was significant because it provided evidence about the comet's structural integrity and suggested that interstellar objects might be more robust than some models had predicted. But then came the disappearance. For several weeks, following perihelion, 3I Atlas entered solar conjunction from Earth's perspective. This is a simple geometrical effect where the comet's position in the sky placed it nearly in line with the Sun as viewed from Earth. During solar conjunction, no Earth-based telescope can observe an object because it's lost in the Sun's glare. No Earth-orbiting observatory can see it for the same reason. The comet was still there, still following its calculated trajectory, but from humanity's viewpoint, it had vanished. This period of invisibility created a natural narrative gap in the comet's story. We knew where it had been before conjunction, we knew where it should emerge afterward, but we couldn't watch the transition. This disappearance, purely a result of viewing geometry, and not anything unusual about the comet itself, became fodder for speculation in some corners of the internet. Where did the comet go? Why can't anyone see it? Is NASA hiding something about what happened during those weeks when the comet was behind the Sun? These questions, while understandable from people not familiar with the mechanics of solar conjunction, revealed an important truth about how astronomical events get interpreted through different filters. For astronomers, solar conjunction is routine, an expected and well-understood phenomenon that happens regularly with planets, comets, and other solar system objects. For the general public encountering this information without context, it could sound suspicious, as if something was being concealed. The reality was far less dramatic. The comet continued on its path, invisible to us simply because we couldn't look toward the Sun without being blinded by its light. Spacecraft like SOHO could observe it during the period immediately around perihelion because they have instruments specifically designed to block the Sun's disk and observe the corona. But as the comet moved away from its closest solar approach and into conjunction, even SOHO couldn't track it anymore. The comet was moving through a blind spot in humanity's observational capabilities, following a trajectory we had calculated precisely, expected to emerge on the other side of the Sun in mid-November, exactly where predictions said it would appear. And emerge it did. By mid-November, the geometrical alignment changed. The comet moved far enough from the Sun's position in Earth's sky that telescopes could begin searching for it again. Professional observatories and amateur astronomers equipped with high-quality equipment turned their instruments toward the calculated coordinates, waiting to reacquire the interstellar visitor and continue documenting its journey outward through the solar system. The comet was there, right where it was supposed to be, continuing on its hyperbolic path that would carry it past Earth in December and then outward toward the outer solar system and eventually back to interstellar space. But the comet that emerged from conjunction wasn't quite the same as the one that had entered it. Observers noted changes in its appearance, variations in brightness, modifications to its tail structure. These changes weren't necessarily surprising. Comets are dynamic objects that respond to solar heating in complex ways. As the distance from the Sun increases after perihelion, the intensity of solar radiation decreases, which affects how much ice vaporizes from the comet's surface and how much gas and dust gets released into the coma and tail. The changes observed in 3I Atlas were consistent with a comet moving away from the Sun and gradually becoming less active as it cooled. But they were also data points that needed explanation, observations that astronomers would use to refine their models of how interstellar comets behave compared to their solar system counterparts. Ground-based observations picked up details that spacecraft observations had missed. Telescopes captured the comet's ion tail, a stream of ionized gas extending in the direction away from the Sun, glowing with the characteristic blue color that comes from carbon monoxide and other molecules being excited by solar ultraviolet radiation. They also documented an antitail, an optical illusion that sometimes appears with comets where dust particles ejected from the comet appear to create a tail pointing toward the sun. This is actually a perspective effect where we're seeing the dusty plane of the comet's orbit edge, but it creates striking images and provides information about how dust is being distributed around the comet's nucleus. Each observation added depth to our understanding of 3I Atlas. Each image contributed to the database astronomers were building about this interstellar visitor. And each piece of data raised questions that pushed scientific understanding forward. How does the composition of an interstellar comet compare to comets formed in our solar system? What does this tell us about the processes of planetary system formation around other stars? How common are these interstellar visitors, and how many might be passing through our solar system undetected because they're too faint or in positions where we're not looking? These questions don't have simple answers, but the observations of 3I Atlas during its journey toward December 19th provide clues that help astronomers formulate better questions and design better observations for future interstellar visitors. Now, as the comet continues its outward journey from the Sun, it's simultaneously approaching its closest point to Earth. The trajectory is well mapped. The date is fixed. December 19th represents the intersection of the comet's path through space, with the position in Earth's orbit where we'll be at that moment. It's not a collision course. It's not even close to one. But it's the nearest approach this interstellar object will make to our planet before it leaves the solar system forever. And that proximity, combined with the comet's unique origin, makes December 19th a date of genuine astronomical significance worth understanding in detail, which is exactly where we need to go next, into the specific observations that have shaped our understanding of this visitor and what they reveal about the bigger picture of our place in a galaxy, filled with wandering objects we're only just beginning to notice. The observations NASA's spacecraft made of 3I Atlas tell a story that goes deeper than simple documentation of a comet's passage. Each image, each data point represents an opportunity that scientists seize to learn something new about an object that formed in conditions we've never directly observed. When you look at the accumulated observations from Mars orbiters, from deep space missions, from solar observatories, you're seeing the results of a distributed intelligence network that spans the solar system, opportunistically gathering information whenever a target of interest comes within range. This is modern astronomy at work, not just single telescopes and lone observers, but coordinated efforts leveraging every available asset to maximize scientific return. The Mars observations deserve particular attention because of their proximity advantage. While the comet never came close enough to Mars to present any hazard to the planet or its orbital infrastructure, the geometry of the inner solar system in October placed Mars at a position where spacecraft orbiting the planet had relatively favourable viewing angles of 3I Atlas during its approach toward perihelion. The high-resolution imaging science experiment, HiRISE, aboard the Mars Reconnaissance Orbiter typically focuses on mapping the Martian surface at unprecedented resolution. But mission planners recognized the value of turning this powerful camera toward the interstellar visitor passing through the neighborhood. What HiRISE captured were images showing 3I Atlas as a faint, fuzzy object with a visible tail extending away from the Sun. These weren't portraits of the nucleus itself, which remained too small and distant to resolve as anything more than a point source, even with HiRISE's impressive capabilities. But the coma and tail were clear, providing visual confirmation of the comet's active state. The images also served an important calibration purpose. By comparing observations from Mars orbit with simultaneous observations from Earth, astronomers could use parallax, the apparent shift in position due to different viewing angles, to refine distance measurements and orbital calculations. Every additional data point improved the precision with which the comet's trajectory could be predicted, including the exact parameters of its December 19th approach to Earth. The Psyche spacecraft's observations came from a very different vantage point. Psyche launched in October 2023 on a mission to study a metal-rich asteroid in the main belt, representing a journey into a realm of the solar system where few spacecraft have ventured. By the time 3I Atlas was making its perihelion passage, Psyche was already far from Earth, positioned in a way that gave it a unique perspective on the comet's trajectory. The spacecraft's images, designed primarily for asteroid surface mapping, were repurposed for comet observation. The resulting images added another angle to the stereoscopic view astronomers were constructing of the interstellar visitor. What makes these multi-spacecraft observations valuable isn't just the accumulation of images, it's the way different perspectives allow scientists to construct three-dimensional models of the comet's coma and tail structure. From a single viewpoint, a comet appears as a two-dimensional projection against the background of stars. But with observations from multiple spacecraft at different locations in the solar system, astronomers can use geometry to reconstruct the actual spatial distribution of gas and dust around the nucleus. This reveals asymmetries, jets of material erupting from specific locations on the nucleus, and patterns in how solar radiation and the solar wind shape the tail. All of this information contributes to understanding the comet's composition, rotation, and how it's responding to the intense environment of the inner solar system. Lucy's contribution came from yet another position, as it travels on a complex trajectory designed to encounter multiple Trojan asteroids over the next decade. Like Psyche, Lucy wasn't originally tasked with comet observations, but the opportunity was too valuable to ignore. The spacecraft's instruments captured data that complemented what other observers were seeing, adding to the comprehensive database being assembled about Threos, Atlas. Each mission contributed what it could based on its position, its capabilities, and its available observing time between primary mission activities. This opportunistic approach to science represents one of the hidden values of having multiple spacecraft distributed throughout the solar system. They become an observing network that can be mobilized when interesting targets appear. The SOHO observations hold a special place in this collection of data because they captured 3I Atlas at the most critical phase of its journey, the perihelion passage when the comet was closest to the Sun and experiencing maximum heating and radiation exposure. SOHO's LASCO C3 coronagraph, designed to observe the outer solar corona and track coronal mass ejections that can affect Earth's magnetic field, has an unexpected secondary career as a comet observer. Since its launch in the late 1990s, SOHO has discovered more comets than any single mission or observatory in history, mostly small sun-grazing comets that pass so close to the Sun they're destroyed by the encounter. 3I Atlas was different from SOHO's typical comet discoveries. It wasn't a sun-grazer. Its perihelion distance was large enough that the comet remained well outside the Sun's destructive inner regions. But it also meant the comet would be much fainter in SOHO's images, potentially too faint to detect given the bright background of the corona and the comet's distance from the instrument. The fact that SOHO successfully captured 3I Atlas was a small triumph of observation, confirming predictions about the comet's trajectory and providing visual evidence of its survival through perihelion. The images showed the comet with its tail streaming away from the Sun, exactly as expected from solar radiation pressure acting on the dust and gas in the coma. These SOHO images also revealed something about the comet's activity level. The brightness of a comet in images depends partly on the size of its nucleus, but more significantly on how actively it's releasing gas and dust. A dormant comet, one whose ices are locked beneath an insulating layer of dust, can pass through the inner solar system relatively invisibly. An active comet, one that's venting significant amounts of material as solar heat vaporizes surface ices, creates an extensive coma and tail that makes it much more visible, despite having a relatively small nucleus. The fact that 3I Atlas was bright enough for SOHO to detect indicated active outgassing, confirming that this interstellar visitor contained volatile ices that responded to solar heating in ways similar to native solar system comets. The PUNCH mission, the polarimeter to unify the corona and heliosphere, launched in April 2025, added another perspective to the observations. PUNCH was designed to study the solar wind and how it flows outward from the Sun, filling the solar system with a stream of charged particles that shapes the environment every planet experiences. But PUNCH's wide-field images also make it excellent for tracking objects moving through the inner solar system. The mission captured images of 3I Atlas that complemented what SOHO was seeing, providing additional data about the comet's tail structure and how the solar wind was interacting with the gas streaming from the nucleus. What emerged from all these observations was a detailed portrait of an interstellar comet behaving in ways that were simultaneously familiar and subtly different from solar system comets. The familiarity came from the basic physics of how ice and dust respond to solar radiation. Those processes are universal. It doesn't matter whether a comet formed around our Sun or another star. When it gets heated, ices vaporize, gas escapes, dust gets lofted into space, tails form. But the differences appeared in the details, in the composition revealed by spectroscopy, in the exact ratios of different molecules in the coma, in subtle structural features that suggested this object might have a different formation history than comets native to our solar system. Ground-based observatories around the world added their own observations to this accumulating database. Professional telescopes in Chile, Hawaii, Arizona, and other premier observing sites captured high-resolution spectra that broke down the light from the comet into its component wavelengths, revealing the chemical fingerprints of the molecules present in the coma. Amateur astronomers with sophisticated equipment contributed their own images, sometimes capturing details that larger telescopes missed simply because of timing or weather conditions. The astronomy community, professional and amateur alike, recognized the value of documenting this interstellar visitor as thoroughly as possible during its brief period of observability. The ion tail observations deserve special mention. Ion tails are one of the most visually striking features of active comets, often appearing bright blue in color photographs due to emission from ionized carbon monoxide. Unlike dust tails, which are pushed away from the sun by the physical pressure of sunlight hitting dust grains, ion tails are shaped by the sun's magnetic field embedded in the solar wind. The charged particles in the solar wind interact with ionized gas from the comet, pulling the ions along with the wind's outward flow. This creates a tail that points almost exactly away from the sun, regardless of the comet's direction of motion. For 3I Atlas, the ion tail was clearly visible in many observations, indicating substantial gas production and providing a tracer for studying how the solar wind was interacting with material from an interstellar source. The anti-tail phenomenon that appeared in some images created visual interest and provided additional scientific information. Anti-tails aren't real tails pointing toward the sun, which would violate the physics of how radiation pressure and solar wind work. Instead, they're perspective, effects that occur when Earth passes through the plane of a comet's orbit. Dust grains ejected from the comet spread out along the orbital path, and when we view this dusty plane edging, it appears as a spike or tail pointing in a direction that seems wrong. The presence of an anti-tail in images of 3I Atlas told astronomers about the spatial distribution of dust around the comet, and provided data about the size and velocity distribution of dust grains being ejected from the nucleus. All these observations from spacecraft across the solar system and telescopes around the world created a comprehensive dataset about 3I Atlas that rivals or exceeds what we know about many periodic comets that have been studied for decades. This is the new era of astronomy, where networking, rapid communication, and the ability to mobilize observing resources quickly allow the community to respond to unexpected events with coordinated campaigns that maximize scientific return. And what this coordination revealed about 3I Atlas was an object that justified the attention it received, a genuine interstellar visitor that survived its passage through our inner solar system and continues outward toward its December 19th encounter with Earth's vicinity, carrying with it information about conditions in another stellar system encoded in its composition and structure, information that observations during closest approach will help astronomers decode and understand. Which brings us to the question that has been hovering over this entire investigation. What exactly is going to happen on December 19th? And why does it matter? When an unusual astronomical event captures public attention, a predictable pattern emerges. Official sources provide technical information focused on scientific aspects and risk assessment. Media outlets translate this information for general audiences, sometimes oversimplifying or sensationalizing in the process. And somewhere in the gaps between official statements and public understanding, speculation begins to circulate. For 3I Atlas and its December 19th close approach, this pattern has played out exactly as you might expect, with rumours and questions appearing online that demand thoughtful responses rather than dismissive rejection. Because here's something important. Asking questions about unusual cosmic events isn't foolish. It's exactly what we should do. The key is distinguishing between questions that have solid answers and speculation that has moved beyond what evidence supports. Let's address the biggest misconception first. Some discussions online have suggested that 3I Atlas was hidden during its perihelion passage, implying deliberate concealment by space agencies or observatories. This claim misunderstands the concept of solar conjunction. The comet wasn't hidden by human action. It was hidden by geometry. When an object passes nearly between Earth and the Sun, or on the opposite side of the Sun from Earth's perspective, it becomes impossible to observe with Earth-based or Earth-orbiting instruments because it's lost in the Sun's overwhelming glare. This is basic physics, not conspiracy. The Sun is unimaginably bright. Its light drowns out everything around it in the sky. You can't point a telescope at something close to the Sun's position and expect to see anything except the Sun's light scattering through your optics and destroying your ability to observe faint objects. This happens regularly with planets, comets, and asteroids. Mars goes through solar conjunction approximately every 2 years, when its orbit carries it to the opposite side of the Sun from Earth. During these periods, we can't communicate with Mars rovers and orbiters because the Sun blocks radio signals. Venus and Mercury go through conjunctions even more frequently because of their faster orbits. Comets passing through the inner solar system often experience periods of invisibility when they're too close to the Sun's position in our sky. This is routine astronomy, predictable based on orbital mechanics, and in no way indicative of anything being concealed. The comet didn't disappear. Our ability to observe it was temporarily blocked by the brightest object in our solar system. SOHO's observations during perihelion actually prove this point. The spacecraft was able to see 3I Atlas during the period when it was closest to the Sun precisely because SOHO has a coronagraph that blocks the Sun's disk, allowing observation of the surrounding region. If there was any concealment happening, these images wouldn't have been released. But they were published openly, shared with the scientific community and the public, because space agencies have no reason to hide observations of comets. The data is scientifically valuable, and the whole purpose of these missions is to advance human understanding of the solar system. Claiming concealment requires assuming motivations that don't align with how scientific institutions actually operate or what they're trying to accomplish. Another area of speculation concerns the comet's trajectory. Some discussions have suggested that 3I Atlas has shown anomalous behavior, unexpected changes in its path that might indicate something unusual about its composition or origin. This deserves careful examination because comet trajectories can indeed change in subtle ways due to outgassing effects. When a comet vents gas into space, that gas carries momentum. The escaping gas creates a tiny rocket effect that can alter the comet's trajectory slightly over time. For some comets, these non-gravitational forces are significant enough to require constant updates to orbital predictions. The question is whether 3I Atlas has shown trajectory changes beyond what would be expected from a comet of its activity level. The answer from astronomers who specialize in orbital mechanics is that 3I Atlas's trajectory has been remarkably predictable. Observations match gravitational predictions very closely. Any outgassing effects are small enough that they fall within the normal range for a comet of this size and activity level. The path that brought it to perihelion, through solar conjunction, and toward its December 19th Earth encounter has followed the hyperbolic orbit calculated from early observations with a precision that confirms our understanding of the forces acting on it. There's nothing anomalous here, nothing that requires explanations beyond standard comet physics. The trajectory is exactly what you'd expect from an interstellar object passing through the inner solar system under the influence of the Sun's gravity, with minor perturbations from outgassing. Questions about the comet's composition represent a more legitimate area of scientific inquiry. Interstellar objects might have compositions that differ from solar system natives because they formed under different conditions around different stars. The molecular ratios observed in 3I Atlas's coma, the gases being released as solar heat vaporizes surface ices, provide clues about the environment where this comet formed. So far, spectroscopic observations have shown that the comet's composition isn't dramatically different from solar system comets. It contains water ice, carbon monoxide, carbon dioxide, and other molecules familiar from studies of comets formed around our Sun. But subtle differences exist, ratios that vary slightly from typical values, hints that this object might have experienced a formation environment with different temperatures or radiation levels than the region where our comets originated. These compositional questions are exactly what scientists are investigating. They're not hiding unusual findings, they're actively publishing results and discussing what the data means. The scientific process involves careful analysis, peer review, and gradual refinement of understanding as more observations accumulate. What might seem like evasiveness is actually rigor. Scientists won't claim definitive conclusions when data is still being analysed. They'll present preliminary findings acknowledge uncertainties, and wait for additional observations to confirm or refute initial interpretations. This careful approach is a feature, not a bug. It's how science avoids jumping to conclusions that later prove incorrect. The threat assessment is another area where clear communication is essential. 3i Atlas poses absolutely zero danger to Earth. The distance at closest approach on December 19th is vast by any meaningful standard. The comet will pass at a distance that keeps it far beyond the Moon's orbit, well outside the region where any gravitational influence on Earth would be detectable. Even if the trajectory calculations were somehow wrong, which they're not given the precision of modern orbital mechanics, the comet would have to be orders of magnitude off course to present any hazard. This isn't speculation or optimistic hope. It's mathematical certainty based on observations that have tracked the comet's position with extraordinary accuracy. Understanding this safety margin is important because it allows us to focus on what actually matters about December 19th, the scientific opportunity, not manufactured danger. Comets don't need to be threatening to be interesting. The value of this encounter isn't that we're narrowly avoiding catastrophe. The value is that we're witnessing a visitor from beyond our solar system at the closest range any confirmed interstellar comet has approached Earth, giving us observational opportunities that will teach us about conditions in other stellar systems. Framing this event around threat assessment misses the point entirely. The real story is about discovery, not danger. That said, acknowledging safety doesn't mean we should dismiss every question about what will happen on December 19th. There are legitimate uncertainties about what observations will reveal. Will the comet's brightness match predictions, or will it be fainter or brighter than expected based on its distance and activity level? Will ground-based observers be able to detect it visually, or will it require large telescopes and sensitive cameras? How will its appearance change during the days around closest approach as viewing geometry shifts? These questions don't have definitive answers until the event actually occurs, and that's fine. Not knowing exactly what we'll observe is different from facing danger or being misled about the situation. The brightness predictions are particularly uncertain because comet behavior is notoriously difficult to forecast. The amount of gas and dust a comet produces depends on factors that are hard to model precisely. The composition of surface ices, how deeply the sun's heat penetrates into the nucleus, whether there are active regions or jets producing more outgassing than other areas, and how the comet's rotation affects which regions face the sun at any given time. A comet predicted to reach a certain brightness might surprise astronomers by being significantly brighter or fainter, depending on how these factors play out. For 3i Atlas, predictions suggest it will remain faint, visible through telescopes but not to the naked eye. But those predictions come with uncertainty ranges that acknowledge the unpredictable nature of comet activity. This unpredictability is actually part of what makes the December 19th observation valuable. By comparing predictions with actual observations, astronomers refine their models of comet behavior. If 3i Atlas is brighter than expected, that tells us something about how efficiently its surface ices are converting solar heat into outgassing. If it's fainter, that might indicate a dust mantle covering the nucleus and insulating ices from solar radiation. Either outcome provides data that improves understanding. The uncertainty isn't a problem to be eliminated, it's part of the scientific process. What we can say with confidence is that December 19th represents a real astronomical event with real scientific value, free from the dramatic conspiracy narratives that sometimes attach to cosmic phenomena. The comet is exactly what observations indicate, an interstellar visitor following a predictable path through the solar system. The observations made by NASA spacecraft and ground-based telescopes show an object behaving in ways consistent with comet physics, with no anomalies that require exotic explanations. The safety assessment is solid, based on precise orbital calculations that have been verified through months of tracking. And the questions that remain unanswered are the interesting scientific ones about what we'll learn from this encounter, not questions about hidden dangers or concealed information. With that foundation of fact established, we can turn to what December 19th will actually bring, the specific details of closest approach and what it means for observers around the world who want to participate in witnessing this interstellar visitor's passage through our cosmic neighborhood, which is exactly where the story gets most compelling, because this is when theory meets reality and predictions face the test of actual observation. December 19th arrives in the solar system's calendar with precise inevitability, The date is fixed by the intersection of two paths: Earth's orbit carrying us through our annual circuit around the Sun, and 3i Atlas's hyperbolic trajectory cutting through the solar system on its one-time passage from interstellar space back to interstellar space. These paths don't intersect in the sense of collision. They pass each other at a distance that preserves the safety of both worlds, but achieves a proximity that, by the standards of astronomy and the scales of space, represents a significant close approach worth observing, measuring, and understanding before the opportunity vanishes forever. The geometry of closest approach puts 3i Atlas at a distance from Earth substantially greater than the distance between Earth and the Sun, but substantially less than the distance to most objects that capture astronomical attention. It will pass outside the orbit of the Moon, beyond the region where Earth's gravity has significant influence, but close enough that ground-based telescopes of professional caliber and well-equipped amateur instruments should be able to detect it and track its motion against the background stars. This is the sweet spot for astronomical observation, distant enough to be safe, close enough to be scientifically valuable. What will actually happen during those hours when the comet reaches its minimum distance is straightforward in physical terms but profound in implication. The comet will continue its outward journey, moving away from the Sun at a velocity that confirms its interstellar origin. From Earth's perspective, it will appear as a faint fuzzy object, possibly showing a tail if its activity level remains high enough, moving slowly across the sky over the course of days and weeks. The motion won't be visible to the human eye in real time. You can't watch the comet zip across the sky like a meteor, but photographs taken hours or days apart will show its changing position relative to the fixed background of distant stars, revealing the comet's trajectory through our cosmic neighborhood. For astronomers, December 19th represents the peak opportunity to gather data about this interstellar visitor. Observatories worldwide will be tracking the comet, collecting spectra that reveal its chemical composition, measuring its brightness to determine activity levels, photographing its coma and tail structure to understand how it's responding to the solar environment at this distance from the Sun. Every observation adds to the limited data set we'll ever have about this object, because unlike periodic comets that return regularly allowing repeat observations, 3i Atlas will pass through our observational range exactly once. What we learn from this encounter is what we'll have to work with when trying to understand what this visitor reveals about interstellar space and the environments around other stars. The Virtual Telescope Project, an astronomy outreach initiative that regularly hosts online observations of significant celestial events, has announced plans to conduct a live observation session of 3i Atlas around the time of closest approach. This represents an opportunity for people worldwide who don't have access to telescopes or who live in regions where weather or light pollution prevents personal observation to still participate in witnessing this cosmic encounter. The livestream will show real-time views of the comet captured through professional-grade telescopes, with commentary explaining what's being observed and why it matters. This kind of public engagement transforms astronomy from an exclusive activity of credentialed professionals to a shared human experience accessible to anyone with internet access and curiosity about the universe. What you'll see during such an observation isn't dramatic in the sense of explosions or collisions or sudden changes. It's dramatic in a different way, the drama of realizing you're looking at something that came from beyond the boundary of our solar system, that traveled through the darkness between stars, that formed in orbit around a different sun under conditions we can only infer. That small, faint, fuzzy patch in the telescope's field of view represents a physical connection to the broader galaxy, evidence that our solar system isn't isolated but part of a dynamic environment where objects move between stellar systems, carrying with them information about the diversity of conditions that exist in different regions of the galaxy. That's the true nature of what December 19th offers, not spectacle, but significance. The observational window extends beyond the single date of closest approach, the days before and after December 19th provide opportunities to track the comet's changing appearance as distance and viewing geometry shift. Observers taking photographs across multiple nights can create sequences showing how the comet moves, how its brightness varies, how the tail structure evolves. These amateur contributions to science aren't trivial. Throughout history, amateur astronomers have made significant discoveries and provided observations that professional observatories missed due to weather, telescope availability, or simple timing. The distributed network of observers worldwide ensures that someone, somewhere is likely to capture important data even if conditions aren't perfect at any single location. For someone wanting to observe 3i Atlas personally, the requirements are modest but specific. The comet isn't bright enough for naked eye visibility under most circumstances. Predictions suggest it will remain faint enough that binoculars or a small telescope will be necessary to detect it. Light pollution matters significantly. From a dark rural location far from city lights, a moderately sized telescope can reveal details that would be impossible from an urban or suburban setting. Knowing exactly where to look is crucial, because the sky is vast and a faint comet is easy to miss if you're searching the wrong region. Astronomy apps and websites provide finder charts showing the comet's position relative to brighter stars and constellations, guiding observers to the correct field of view. Photography offers advantages over visual observation for faint objects like 3i Atlas. A camera sensor or dedicated astronomy detector can integrate light over long exposure times, accumulating photons until faint objects become visible that would be impossible to see with the human eye even through a large telescope. This is how many amateur astronomers contribute images to the astronomical community, not by having the largest telescopes, but by having good equipment, dark skies, clear weather, and the patience to take multiple exposures that can be stacked and processed to reveal subtle details. The democratization of astronomy through affordable high-quality cameras and processing software has expanded the community of active observers contributing to science. What won't happen on December 19th is equally important to understand. The comet won't suddenly brighten into a spectacular naked-eye object visible to everyone. Comets can undergo brightness outbursts, but predicting these is essentially impossible, and there's no evidence suggesting 3i Atlas is likely to experience such an event. The comet won't pose any danger to satellites, spacecraft, or Earth itself. The distance is too great for gravitational effects or physical impacts. The comet won't change course or do anything unexpected based on what we understand about comet behavior and the forces acting on objects in the solar system. It will simply continue on its calculated path, following the trajectory that orbital mechanics determines. This might sound anticlimactic after all the build-up. Where's the drama? Where's the unexpected discovery that changes everything? The truth is that science usually progresses through incremental advances, not dramatic revelations. The value of observing 3i Atlas isn't that it will overturn established physics or reveal something incomprehensible. The value is that it adds one more data point, one more example, one more case study to the small but growing collection of interstellar objects we've been able to observe and characterize. Each interstellar visitor teaches us something. Oumuamua showed us that interstellar objects could be much smaller than expected and possibly non-volatile. Comet Borisov demonstrated that some interstellar visitors are clearly comets, with compositions similar to our own comets. 3i Atlas adds to this knowledge base, contributing its own set of observations and measurements that help astronomers understand the range of objects that exist in interstellar space. The closest approach distance, while large by everyday standards, represents something significant in the context of interstellar objects. It's the nearest confirmed interstellar comet approach to Earth in recorded history. That matters because proximity affects observational quality. Closer objects appear brighter and larger, allowing more detailed observations with given instruments. The difference between observing something at this distance versus observing it twice as far away might seem like a small change, but it translates to significant differences in how much light reaches our telescopes, how much detail we can resolve, and how much data we can extract from observations. December 19th offers the best opportunity we'll have to study this particular interstellar visitor, better than any opportunity we'll have before or after, because of the specific geometry of this date. After December 19th, 3i Atlas will continue moving away from both Sun and Earth. Its brightness will fade as distance increases, making it progressively more difficult to observe. Within weeks to months, it will drop below the detection threshold of all but the largest professional telescopes. Within a year or two, it will be gone completely from our observational capability, too faint and too distant for even the most sensitive instruments to track. This is the nature of hyperbolic orbits. Objects following them pass through the solar system once and never return. There's no second chance, no future opposition when viewing conditions might be better. December 19th and the surrounding weeks represent our entire observational window for this object, compressed into a brief interval that demands we take advantage of every clear night and every available telescope. The pressure to observe during this limited window creates urgency in the astronomical community. Telescope time on major observatories is precious, allocated months in, advanced based on proposals judged for scientific merit. Getting observing time for an unexpected target like an interstellar comet requires special arrangements, discretionary time, or reprioritization of scheduled observations. The fact that observatories worldwide are making these arrangements demonstrates the value the scientific community places on interstellar object studies. These objects are rare enough and scientifically interesting enough that when one appears, it's worth disrupting normal schedules to ensure comprehensive observations. What emerges from all this is a picture of December 19th as a date of genuine scientific significance, marked not by danger or drama in the Hollywood sense, but by the quieter drama of human curiosity encountering something rare and learning what it has to teach. The comet's closest approach represents an opportunity measured not in spectacular visuals, but in data collected, questions answered, and understanding advanced. For anyone wondering whether December 19th deserves attention, the answer depends on what you value. If you need explosions and catastrophe to find something interesting, this event won't satisfy you. But if you find meaning in the patient work of understanding the universe, in the accumulation of knowledge through careful observation, in the recognition that we're part of something larger than our planet or even our solar system, then December 19th offers exactly the kind of moment worth noting, worth observing if you can, and worth remembering as the date when an interstellar visitor passed close enough for us to glimpse details of its journey and composition before it returned to the darkness between stars, which raises a different kind of question. Not what will happen on December 19th, but why it matters that this happens at all, what significance we should attach to these rare encounters with visitors from beyond our cosmic neighborhood, which is precisely the territory we need to explore next to understand the deeper implications of this event. The importance of December 19th extends far beyond the specific observations that will be made during those hours when 3i Atlas reaches its closest point to Earth. What matters more than the data collected on any single date is what this encounter represents in the larger context of humanity's evolving understanding of our place in the galaxy. For most of human history, we understood the solar system as a closed system, bounded by the orbit of the outermost planet, containing a fixed population of objects that orbited the Sun in predictable patterns. The idea that objects from other star systems might pass through our cosmic neighborhood wasn't seriously considered because we had never observed such a thing happening and had no strong reason to believe it occurred frequently enough to matter. That understanding has changed fundamentally in the last decade. The detection of Oumuamua in 2017 marked a watershed moment, the first confirmed observation of an object from beyond our solar system passing through our region of space. It was strange, cigar-shaped or possibly pancake-shaped, depending on how you interpreted the limited observations, tumbling as it moved through the inner solar system, showing no obvious comet activity despite coming close enough to the Sun that ices should have vaporized if they were present. The name given to it, Oumuamua, means scout or messenger in Hawaiian, reflecting its role as the first of its kind to be recognized and studied. Its discovery immediately raised questions. How common are these interstellar visitors? What can they tell us about the environments around other stars? And how many have passed through our solar system undetected simply because we weren't looking in the right places at the right times? Comet Borisov, discovered in 2019, provided a different data point. Unlike Oumuamua, Borisov was clearly a comet, showing obvious outgassing and developing a coma and tail as it approached the Sun. Its composition, studied through spectroscopy during its passage through the inner solar system, revealed molecules familiar from solar system comets, suggesting that comet formation might follow similar processes around different stars. Borisov's orbit was less unusual than Oumuamua's trajectory, but still clearly hyperbolic, confirming its interstellar origin. The object passed through perihelion, survived the encounter, and continued outward, fading from view as it left our observational range. It was the second confirmed interstellar object, arriving just 2 years after the first, hinting that these visitors might be far more common than anyone had imagined. 3i Atlas represents the third confirmed interstellar object, detected and confirmed within 8 years of the first discovery. If you assume that observational capabilities have remained relatively constant during this period, which isn't quite true because surveys are actually improving, this suggests that interstellar objects of detectable size might pass through the inner solar system every few years on average. The number that pass through the outer solar system, too distant and faint to be detected with current instruments, is certainly higher. And the number of objects that pass through the broader region of space influenced by the Sun's gravity, but never come close enough to be observed, is higher still. We're beginning to realize that the solar system exists in a kind of interstellar traffic zone where objects from other stellar systems pass through regularly on timescales far shorter than orbital periods of planets. This realization changes how we think about the solar system's boundaries and its relationship to the galaxy. The traditional view of a solar system as an isolated bubble, separate from other stellar systems, no longer holds. Instead, we're recognizing that material exchanges between stellar systems occur routinely on astronomical timescales. Objects get ejected from planetary systems during gravitational interactions, especially during the chaotic early phases when planets are migrating and orbits are unstable. These ejected objects enter interstellar space, traveling through the galaxy on trajectories that might eventually bring them close to other stars. Some fraction of these objects will pass through the gravitational influence of those other stellar systems, becoming temporary visitors before continuing their journeys. Our solar system participates in this exchange. We eject objects into interstellar space, comets from the Oort clouds scattered by gravitational perturbations, asteroids ejected during the solar system's formation, possibly even planets or planetary fragments from the violent early period, when impacts and close encounters were common. These ejected objects become part of the galaxy's population of free-floating interstellar debris, traveling between stars on timescales measured in millions of years. Some will eventually encounter other stellar systems. Some might be captured into new orbits if conditions are right. Most will simply pass through, experiencing brief gravitational interactions before continuing onward, much like 3I Atlas is doing during its passage through our neighborhood. The scientific value of observing these interstellar visitors lies in what they reveal about conditions around other stars. When we observe a comet like 3I Atlas, we're seeing ices that formed in the outer regions of another planetary system, possibly orbiting a star different from our Sun in mass, temperature, and age. The composition of those ices, the ratios of water to carbon monoxide to carbon dioxide to methane and other volatiles, provides information about the temperature and radiation environment where the comet formed. By comparing these compositions to solar system comets, astronomers can infer whether planetary system formation follows similar patterns around different types of stars or whether significant variations exist depending on stellar properties. The structure of interstellar comets also matters scientifically. How tightly bound is the nucleus? How resistant is it to tidal forces and solar heating? How does its outgassing behavior compare to solar system comets at similar distances from the Sun? These questions about physical structure inform theories of how comets assemble from the dust and ice in protoplanetary disks. If interstellar comets consistently show different structural properties than solar system comets, that would suggest variations in the formation process. If they're similar, it would support the idea that comet formation follows universal patterns determined by physics rather than by specific circumstances of individual planetary systems. Beyond the technical scientific questions, interstellar objects carry philosophical significance. They remind us that planetary systems aren't isolated islands separated by unbridgeable gulfs of empty space. They demonstrate that the galaxy is a more connected place than our everyday experience suggests, with material moving between stellar systems, carrying information encoded in composition and structure about the diversity of environments where planets and comets form. When we observe 3I Atlas, we're not just seeing a comet, we're seeing evidence of this connectivity, proof that our Sun's gravitational influence creates a kind of net that captures samples from other regions of the galaxy, allowing us to study material that formed light years away under conditions we cannot directly observe. This perspective transforms how we think about searching for life in the universe. If material regularly moves between stellar systems, then the possibility exists that biological molecules or even microbial life could be transported between worlds in a process called panspermia. While there's no evidence that this has occurred, the mere fact that interstellar objects pass through planetary systems regularly enough that we've now detected 3 in 8 years suggests that the exchange of material between stellar systems isn't negligibly rare. It happens. The question is what that exchange means for the distribution of complex chemistry or biology across the galaxy. The observation of interstellar objects also drives technological and methodological advances in astronomy. Detecting these visitors requires survey systems that can scan large areas of sky repeatedly, looking for objects that move against the background of stars. The same surveys that find interstellar objects also detect asteroids that might pose impact hazards to Earth, comets making their first passage through the inner solar system, and other transient phenomena that would be missed by telescopes focused on small fields of view. The development of wide-field survey capabilities, automated detection algorithms, and rapid follow-up observation networks benefits multiple areas of astronomy, all driven partly by the desire to find and characterize interstellar visitors during their brief periods of visibility. Each interstellar object observed provides constraints on theoretical models of how many such objects exist in interstellar space. If we detect 3 in 8 years, and we know roughly what fraction of sky we're surveying with what sensitivity, we can estimate the total population of interstellar objects passing through the inner solar system at any given time. Those estimates feed into models of planetary system formation and evolution, helping astronomers understand how efficient the ejection process is and what fraction of material formed in planetary systems ends up wandering through interstellar space. These are fundamental questions about how the galaxy works, answered partly through observations of objects like 3I Atlas. The December 19th encounter with 3I Atlas contributes to this larger scientific program. The observations made during closest approach add to the limited database of interstellar object characterizations. The data collected will be analyzed compared to previous interstellar visitors and to solar system comets, and used to refine our understanding of comet formation and interstellar object properties. The work isn't glamorous in the way that discovering a potentially habitable planet is glamorous. It's the patient accumulation of evidence, the gradual building of knowledge through repeated observations and careful analysis. But this is how science actually advances most of the time, not through dramatic revolutionary discoveries that overturn everything we thought we knew, but through incremental improvements in understanding built on foundations of accumulated data. For anyone watching this video wondering why they should care about a faint comet passing at a safe distance from Earth, this is the answer. You should care because this encounter represents humanity's expanding awareness of the cosmic environment we inhabit. You should care because each interstellar object observed teaches us something we couldn't learn any other way about the diversity of conditions in the galaxy. You should care because the same curiosity that drives astronomers to observe 3I Atlas is the curiosity that has driven every major advance in human understanding of the universe. And you should care because moments like December 19th, when something rare becomes observable, when something from beyond our cosmic neighborhood passes close enough to study, don't come around often, and recognizing their value is part of what it means to be curious about the universe we're part of, which brings us to what happens after December 19th, after closest approach has passed, and the comet continues its journey outward. Because the story doesn't end when the comet reaches its nearest point to Earth. It continues through the weeks and months that follow as the object gradually fades from view, and humanity's window on this interstellar visitor slowly closes. The moment of closest approach on December 19th represents a peak in observational opportunity, but it doesn't mark an ending. The comet's journey through our solar system continues for months and years after it passes Earth, following the hyperbolic trajectory that will eventually carry it back into interstellar space. Understanding what happens during this departure phase is important for grasping the complete arc of 3I Atlas's passage through our cosmic neighborhood, and for appreciating how astronomers squeeze every possible observation from the limited time window when this visitor remains detectable. Immediately after closest approach, the comet will still be relatively well positioned for observation from Earth. The geometry changes daily as both Earth and the comet move through their respective paths, but for several weeks following December 19th, the comet remains close enough and bright enough that professional observatories and well-equipped amateur astronomers can continue tracking it. During this period, observations document how the comet's activity evolves as it moves farther from the Sun. Comets typically become less active as solar distance increases because the Sun's heat becomes less intense, vaporizing fewer ices from the comet's surface. For 3I Atlas, already moving away from the Sun after passing perihelion in October, the trend toward decreasing activity continues through December and into the following months. Watching a comet fade provides valuable scientific information. The rate at which brightness decreases with increasing solar distance depends on the comet's composition and structure. A comet with mostly water ice on its surface fades quickly once it moves beyond the distance where solar heat is intense enough to efficiently vaporize water. A comet with more volatile ices, substances that vaporize at lower temperatures like carbon monoxide or carbon dioxide, might remain active at greater solar distances, fading more slowly than a water-dominated comet. By monitoring how 3I Atlas's brightness changes during the weeks and months after December, astronomers learn about which ices are present on its surface and how deeply the Sun's heat has penetrated into the nucleus during the comet's passage through the inner solar system. The comet's path takes it outward through the inner solar system during January and February, moving away from both the Sun and Earth, but remaining within the observational range of major telescopes. By March, it will have passed beyond the orbit of Mars, entering the asteroid belt region, where solar distance is large enough that only the most volatile ices continue to outgaze at significant rates. Through spring and into early summer, the comet continues its outward journey, gradually fading as distance from the Sun reduces the intensity of solar radiation heating its surface. Professional observatories continue tracking it as long as it remains bright enough to detect, extending the observational baseline and allowing refinement of the orbital trajectory calculations. By the time 3I Atlas reaches the distance of Jupiter's orbit in spring 2026, it will have faded to the point where only the largest telescopes can detect it, and even then only with difficulty. At this distance, the Sun appears more than 20 times fainter than it does from Earth, providing barely enough heat to drive any remaining comet activity. The object transitions from active comet to dormant body, its ices sealed beneath an insulating layer of dust that prevents further significant outgassing. From this point onward, what astronomers observe isn't a comet in the traditional sense of an object with a visible coma and tail, but simply the bare nucleus, a small dark body reflecting only a tiny fraction of the already weak sunlight reaching it. The tracking continues as long as possible, extracting every last observation before the comet drops below the detection threshold of even the most sensitive instruments. These final observations serve an important purpose beyond simply watching the comet disappear. They extend the arc of observed positions along the comet's trajectory, allowing more precise calculations of the hyperbolic orbit. The longer the baseline of observations, the better astronomers can determine the comet's original direction of entry into the solar system, and its destination direction as it leaves. These vectors provide clues about where in the galaxy the comet might have originated and where it's headed, information that feeds into models of galactic dynamics and the population of interstellar objects. Eventually, the observations stop. The comet becomes too faint, too distant, too difficult to distinguish from the background stars. The exact date when the last observation occurs depends on telescope availability, weather, and the comet's actual brightness evolution, which can vary from predictions. But sometime in late 2026 or 2027, 3I Atlas will fade from detectability, dropping below the threshold where even the largest telescopes gathering light for hours can distinguish it from the noise of the sky background. At that point, the comet continues its journey unobserved, following the trajectory calculated from the months of tracking data, moving farther from the Sun with each passing year. The path ahead for 3I Atlas spans thousands and then millions of years. The comet will pass beyond the orbit of Neptune, through the Kuiper Belt region where Pluto and similar objects orbit in the cold outer reaches of the solar system. It will continue outward through the scattered disk, the region beyond Neptune where objects have highly elliptical and tilted orbits, remnants from the solar system's formation era, scattered by gravitational interactions with the giant planets. Eventually it will reach the Oort cloud, the vast spherical shell of comets surrounding the Sun, at distances so extreme that the Sun's gravity barely holds them in orbit. But unlike Oort cloud comets, which orbit the Sun and can be perturbed back into the inner solar system by gravitational interactions, 3I Atlas is moving too fast. It will pass through the Oort cloud without being captured, exiting the Sun's gravitational influence entirely. The transition from gravitationally bound to the Sun to truly free in interstellar space isn't sharp. It happens gradually as the comet moves into regions where the Sun's gravity becomes weaker than the gravitational influence of nearby stars and the galaxy as a whole. By the time several tens of thousands of years have passed, 3i Atlas will have travelled far enough that it's more accurate to describe it as an interstellar object again rather than as a visitor passing through our solar system. It will wander through the local region of the galaxy, occasionally passing near other stars, perhaps eventually entering another stellar system millions or billions of years from now where, if that system contains intelligent observers with telescopes, it might be detected and studied just as we detected and studied it during its passage through our neighbourhood. This long-term trajectory highlights the transient nature of our interaction with 3i Atlas. From the Comet's perspective, if such a thing can be said to exist, our solar system is a brief interruption in a much longer journey through the galaxy. The Comet spent potentially millions of years travelling through interstellar space before encountering our Sun's gravity. It will spend a few years passing through the inner solar system, interacting with solar radiation and the solar wind, being observed and measured by curious inhabitants of the third planet. And then it will spend millions more years travelling outward until it encounters something else, or simply continues wandering through the galaxy indefinitely. The December 19th close approach to Earth is a vanishingly small moment in this vast timeline, significant to us because we're here to witness it, but merely one point along a trajectory that stretches across galactic distances and timescales. There's something poignant about this realization. We get one chance to observe this object. The observations we make during its passage through our observational range are the only data we'll ever have about this specific interstellar visitor. Unlike a planet that orbits the Sun and can be observed repeatedly over centuries, unlike a periodic comet that returns allowing successive generations of astronomers to study it with improving technology, 3i Atlas passes through exactly once. What we learn from it is what we learn now, during these months when it's close enough and bright enough to observe. There are no doovers, no opportunities to check our work decades later, when better instruments become available. This creates urgency in the astronomical community and a sense of finality about the observations being conducted. The departure of 3i Atlas, after December, also reminds us that interstellar objects, while rare enough to be special, aren't unique. The comet represents the third confirmed interstellar visitor in 8 years. Surely there will be a fourth, a fifth, a 10th. Each will provide additional data points, expanding our understanding of the population of objects wandering between stars. Each will have its own unique properties, its own trajectory, its own composition, that adds to the mosaic of information about conditions around different stars and in different regions of the galaxy. 3i Atlas is special because it's here now, because it's the current opportunity to observe an interstellar visitor, but it's also part of a larger phenomenon that we're only beginning to recognize and characterize. Looking ahead beyond 3i Atlas's departure, astronomers anticipate that improving survey capabilities will detect interstellar objects more frequently. New telescopes coming online, new automated survey systems, scanning the sky, and new detection algorithms processing the resulting data will find fainter objects at greater distances than previous generations of instruments could detect. The rate of interstellar object discoveries will increase, transitioning from exciting rare events to routine detections that occur multiple times per year. This shift from scarcity to abundance, while it might reduce the novelty of any individual discovery, will provide the statistical sample size needed to answer questions about the population of interstellar objects, their size distribution, their compositional diversity, and their implications for understanding planetary system formation and evolution. But that future abundance doesn't diminish the significance of 3i Atlas in December. This is the interstellar visitor that's here now, the one we can observe, the one whose December 19th close approach represents our best opportunity to gather data before it fades from view. The subsequent discoveries will be valuable, but they'll be separate events with their own opportunities and limitations. Right now, in this moment, 3i Atlas is what we have, the third confirmed interstellar object, making its closest approach to Earth on a specific date that's rapidly approaching, offering us a chance to witness something that connects our local cosmic neighbourhood to the broader galaxy, which raises the question of what that connection means, how it fits into our understanding of the galaxy as a place not of isolated stellar systems, but of interactions and exchanges that link stars separated by light years into a kind of ecosystem where material and possibly even information flows between systems on timescales measured in millions of years, an understanding that fundamentally changes how we think about our place in the cosmos and what it means to be part of something larger than our planet or our star. The story of Three-Eye Atlas extends beyond one comet and one date. It opens a window onto a larger reality about the nature of the galaxy and the solar system's relationship to the broader cosmic environment. For most of history, humanity understood the world as bounded by immediate surroundings, then by the planet, then by the solar system. Each expansion of understanding required recognizing that what seemed like edges or boundaries were actually just limitations of perspective. The realization that interstellar objects regularly pass through our solar system represents another such expansion, a recognition that the boundary between our star system and the rest of the galaxy is permeable, crossed routinely by travelers that connect our cosmic neighborhood to regions of space light years away. Understanding the frequency of interstellar visitors requires grappling with numbers that challenge intuition. Space is vast. The distances between stars are so large that even traveling at spacecraft velocities, crossing from one stellar system to another would take thousands of years with current technology. Light itself, traveling faster than anything else in the universe, requires years to cross these gulfs. Our nearest stellar neighbor, Proxima Centauri, is more than 4 light-years distant. The stars whose names are familiar from constellations and mythology lie dozens to hundreds of light-years away. In this context of immense emptiness, the idea that objects routinely cross between stellar systems seems implausible. How could anything traverse these distances? What could possibly be common enough that we'd detect multiple examples within a few years? The answer lies in understanding the scale of the galaxy and the dynamics of planetary system formation. Stars aren't isolated. The Milky Way contains hundreds of billions of stars, distributed throughout a disk structure with a dense central bulge and spiral arms where star formation occurs. Our Sun occupies a position in one of these spiral arms, surrounded by other stars at distances measured in light years. The nearest stars are close enough that objects moving at typical orbital velocities would take hundreds of thousands of years to travel between them, not the millions or billions of years required to cross the entire galaxy. On the timescale of galactic history, hundreds of thousands of years is brief, a blink compared to the billions of years stars and planets exist. During planetary system formation, objects get ejected from their native systems through gravitational interactions. When planets migrate inward or outward during the chaotic early phases of system evolution, their changing orbits gravitationally scatter smaller bodies, comets and asteroids, and possibly even planets. Many of these scattered objects end up on highly elliptical orbits that remain bound to the star but take them far into the outer reaches of the system. But some fraction receives enough energy from gravitational encounters that they exceed escape velocity, launching them onto trajectories that carry them out of their home system entirely into interstellar space. Once in interstellar space, these ejected objects become independent travelers, moving through the galaxy influenced by the overall gravitational field of the galaxy's mass distribution, but not bound to any particular star. They travel for hundreds of thousands or millions of years, crossing the distances between stars at velocities typical of orbital motion around stars, a few dozen kilometers per second. Eventually, many of these travelers encounter other stellar systems. Most pass through without being captured. Their velocity is too high relative to the new star for gravity to trap them into bound orbits. These are the interstellar visitors we're beginning to detect, objects that originated around other stars passing through our solar system, on journeys that will carry them onward to other eventual encounters. The number of such objects currently passing through the region of space, influenced by the Sun's gravity, likely numbers, in the thousands or more at any given time. Most are too small, too dark, and too distant from the Sun to be detectable with current telescopes. They move through the outer solar system unnoticed, travelling through the Oort cloud region, passing through the Kuiper belt, following trajectories that never bring them close enough to the Sun for solar heating to make them visible as comets. The ones we detect, objects like Oumuamua, Borisov, and Three-Eye Atlas, represent the tip of a much larger population, the few that happen to pass close enough to the Sun and happen to have properties that make them detectable at those distances. This realization transforms how we think about the solar system's boundaries. The traditional picture of a solar system as a bubble with a defined edge, where the Sun's influence ends, doesn't capture the reality of a gradual transition between regions, where the Sun's gravity dominates, and regions where galactic gravity takes over.
Objects in the Oort cloud, the most distant part of the solar system, are so loosely bound to the Sun that passing stars can perturb them, sending some into the inner solar system, where they become long-period comets, and ejecting others into interstellar space where they join the population of wanderers. The boundary is fuzzy, dynamic, and crossed in both directions by objects entering from interstellar space and objects being ejected outward. Living in an interstellar neighborhood means recognizing that our solar system participates in a galactic ecosystem, where material moves between stellar systems, where what happens in one planetary system can eventually affect others through the transfer of physical objects carrying information about conditions in their systems of origin. The implications extend beyond astronomy into questions about the distribution of complex chemistry and potentially biology in the galaxy. If interstellar objects are common enough that we detect several per decade, then over the billions of years of Earth's history, countless such objects have passed through our solar system. Some may have even collided with planets, depositing material from other stellar systems onto planetary surfaces. While there's no evidence this has led to transfer of life between stellar systems, the physical possibility exists in ways that weren't seriously considered before we knew how common interstellar visitors are. The study of interstellar objects also informs our understanding of planetary system diversity. Each visitor carries information encoded in its composition about the environment where it formed, the presence of certain molecules, the ratios between different ices, the structural properties of the nucleus, all provide clues about temperature, radiation levels, and chemical conditions in its birth system. By studying multiple interstellar objects over time, astronomers can begin to map the diversity of conditions in planetary systems throughout the galaxy, complementing the information gained from detecting exoplanets through other methods. Interstellar objects offer a way to study planetary system formation around distant stars through the samples those systems have ejected into interstellar space. The technology being developed to detect and characterize interstellar visitors benefits broader astronomy. Survey systems designed to find fast-moving, faint objects in the sky serve multiple purposes, identifying potentially hazardous asteroids that might impact Earth, discovering comets making their first passage through the inner solar system from the Oort cloud, detecting variable stars and transient events like supernovae, and finding interstellar objects. The development of automated detection algorithms, rapid follow-up observation protocols, and international coordination networks for sharing data about newly discovered objects represents infrastructure that enhances humanity's ability to monitor the dynamic sky and respond to discoveries that require time-sensitive observations. Looking toward the future, the detection rate of interstellar objects will increase as survey capabilities improve. The Vera Rubin Observatory, scheduled to begin operation soon, will repeatedly scan large areas of sky with sensitivity far exceeding previous surveys. Its data stream will identify moving objects, including interstellar visitors, at rates that will make such discoveries routine rather than rare. This transition from novelty to normality is how science typically progresses. The first detection is revolutionary, changing what we know is possible. The next few are exciting, confirming that the first wasn't a fluke, but as the sample grows, the phenomenon becomes normal, integrated into our understanding as an expected feature of the environment rather than a surprising anomaly. This normalization doesn't diminish the significance of interstellar objects. It enhances it by providing the statistical sample needed to answer questions about populations rather than individual examples. How many interstellar objects exist per cubic light-year of space? What are the typical size distributions? Are most of them rocky, icy, or metallic? What fraction originated from systems around stars similar to our Sun versus stars of different masses and ages? These population-level questions require dozens or hundreds of detections to answer confidently. The 3 confirmed interstellar objects detected so far provide tantalizing hints, but not definitive answers. The larger sample coming from future surveys will transform speculation into data-driven conclusions. For 3i Atlas, the role in this larger story is clear. It's one of the early detections that established the reality of interstellar object transits through our solar system. It contributes data to the initial characterization of this population. Its December 19th close approach provides observational opportunities that add to the limited database we currently have about these visitors. As time passes and more interstellar objects are discovered, 3. iAtlas will be remembered as one of the first, an early example that helped define the phenomenon and establish the methods for studying it. This historical context doesn't diminish its immediate significance. It enhances it by connecting this individual event to the broader program of understanding humanity's place in a galaxy that's more dynamic, more interconnected, and more accessible through study than previous generations realized. The philosophical implications of living in an interstellar neighborhood extend beyond science into questions about perspective and meaning. Recognizing that objects from other stellar systems regularly pass through our cosmic backyard changes the sense of isolation that often characterizes thinking about space. We're not alone on an island in a vast empty ocean. We're part of a network, connected to other stellar systems through the flow of material that carries information about conditions throughout our region of the galaxy. This connection doesn't involve communication or intelligence. It's purely physical, the movement of ice and rock through gravitational fields. But it demonstrates that the galaxy operates as an integrated system rather than a collection of isolated components, and that insight shifts how we understand our relationship to the cosmos, which brings us to the personal level, to what December 19th means not for astronomy as a discipline, but for anyone who looks up at the night sky and wonders about what's out there beyond the familiar planets and stars, anyone who wants to connect with this moment when something from beyond our solar system passes close enough to witness, which is where this investigation ultimately needs to arrive, at the human level where cosmic events become personal experiences that shape how we see ourselves and our place in the universe. We've travelled through the story of 3i Atlas, tracing its journey from interstellar space through perihelion and solar conjunction to its December 19th approach to Earth, examining the observations that spacecraft and telescopes have made, separating fact from speculation, and understanding why this encounter matters in the larger context of humanity's expanding awareness of the cosmic environment. Now we arrive at the personal question that makes all this information relevant beyond academic interest. What does December 19th mean for you? How can you connect with this moment? And why should you care about a faint comet passing at a safe distance when the world offers so many immediate concerns competing for your attention? The answer begins with recognizing that December 19th offers something rare, a specific date when something extraordinary happens that connects us to the broader universe in a tangible way. Most cosmic events are either too slow to perceive on human timescales, or too distant to feel relevant. Galaxies collide over millions of years. Stars are born and die, light years away where we can observe the results, but never experience them directly. The universe mostly operates on scales that dwarf human significance, making it easy to feel disconnected from astronomical discoveries, to treat them as interesting facts without personal relevance. But occasionally, the cosmos provides moments that bridge the gap between vast scale and human experience. December 19th is one of those moments. On that date, at a specific calculable time, an object that formed around another star in a different region of the galaxy will reach its closest point to Earth. You'll be on this planet when it happens. Everyone alive will share that moment simultaneously, united by the simple fact of occupying the same world at the same time during this rare geometric alignment. The comet doesn't care, obviously. It's an inanimate collection of ice and rock following physical laws. But you have the opportunity to care, to choose to notice, to mark this date as significant because of what it represents about the kind of universe we inhabit and the kind of beings we are who can recognize and appreciate such moments. The most direct way to engage with December 19th is through observation. If you have access to a telescope, even a modest one, and if you have clear skies and dark conditions, you can try to find 3i Atlas yourself. Astronomy apps and websites will provide finder charts showing exactly where in the sky to look based on your location and the time of night. The comet will be faint, challenging to detect, requiring patience and dark-adapted eyes, or a camera capable of long exposures. But the reward for that effort is direct personal observation of an interstellar visitor, the satisfaction of seeing with your own eyes something that came from beyond the solar system. That's not an experience many people will ever have. Most won't try, most won't know it's possible, but you have that option if you choose to pursue it. If you don't have a telescope, or if weather and conditions aren't favourable for personal observation, the Virtual Telescope Project's planned livestream offers an alternative. You can watch online as professional equipment tracks the comet in real time, seeing what observers at ideal locations with high-quality instruments see, participating virtually in the observation even if you can't conduct it personally. The live stream democratizes the experience, making it accessible to anyone with internet connection, regardless of their equipment or local conditions. This is the power of modern technology applied to astronomy, transforming events that were once accessible only to professionals, with access to observatories, into shared experiences that anyone can witness. Even if you don't observe at all, even if you simply know that December 19th is happening and choose to mark it mentally as the date when an interstellar comet made its closest approach to Earth, that awareness itself has value. It connects you to a moment of cosmic significance. It places you in the story of this comet's journey as a witness who noticed its passage. Years from now, when 3i Atlas has long since faded from view and left the solar system, you'll be able to remember that you were aware during its closest approach that you were part of the global community that noticed this visitor and understood what it represented. That memory becomes part of your personal connection to the larger universe, a touchstone for thinking about your place in the cosmos. The questions December 19th raises don't have simple answers, and maybe that's appropriate. What does it mean that objects from other stellar systems pass through our cosmic neighborhood? What does it tell us about our connection to the rest of the galaxy? How should we think about our relationship to a universe where boundaries are permeable and material moves between regions separated by light years? These aren't questions science can fully answer because they blend factual observation with personal meaning-making. Science tells us that interstellar objects exist and can be detected. It tells us about their compositions, trajectories, and frequencies. But the significance of that information, what it means for how we understand ourselves and our place in the universe, that's something each person constructs individually, based on their own values and perspectives. For some, the scientific value of observing 3i Atlas provides sufficient meaning. The data collected contributes to human knowledge about interstellar objects, planetary system formation, and galactic dynamics. That contribution, even if small, is real and valuable. It advances understanding incrementally, adding to the accumulated knowledge that future generations will build upon. If you find meaning in the patient work of science, in the gradual accumulation of understanding through careful observation and analysis, then December 19th offers exactly that kind of meaningful moment. For others, the significance might be more personal and philosophical. Knowing that you share this moment with everyone else alive, that all of humanity occupies the same planet at the same time as this interstellar visitor, makes its closest approach, creates a sense of shared experience across all the divisions that normally separate people. National borders, cultural differences, political disagreements, all the things that fragment human experience into competing groups become temporarily irrelevant in the face of a cosmic event that affects everyone equally. The comet doesn't distinguish between countries or beliefs. It simply follows its trajectory, indifferent to human concerns but available to anyone who wants to observe it. There's something democratizing about that indifference, a reminder that we're all part of something larger than our local concerns. The December 19th encounter also reminds us of transience and the importance of seizing opportunities when they arise. This comet passes through our observational range exactly once. If you don't notice it now, you'll never have another chance. This isn't like a museum exhibit you can visit next month if you're busy today. It's not like a video you can watch later when you have time. It's a moment that occurs on a specific date and then passes into history, with the opportunity for direct observation vanishing as the comet moves farther from Earth and fades from detectability. This temporal limitation gives December 19th an urgency that makes engagement feel more meaningful than passive consumption of information that will always be available. What I'm asking you to do is simple but significant. Notice December 19th. Mark it somehow. Watch it unfold, whether through personal observation, online live stream, or simply conscious awareness that this is the date when 3i Atlas reaches closest approach. Be part of the community of people worldwide who chose to pay attention to this interstellar visitor during its passage through our cosmic neighborhood. Let this moment become part of your relationship with the universe, a specific date when something from beyond the solar system came close enough for humanity to study it, and you were present for that encounter. And as December 19th approaches, share this story. Tell someone else about the interstellar comet making its closest approach. Explain why it matters. Help expand the community of people who notice these cosmic moments
and recognize their significance. The value of astronomical events isn't limited to the data scientists collect. It includes the broader cultural impact of helping people connect with the universe, understand their place in it, and find meaning in being part of something vastly larger than individual human concerns. You can contribute to that broader impact by being someone who noticed, who cared enough to learn about 3i Atlas, and who shared that knowledge with others. Before you go, help this video reach more people who would care about this cosmic encounter. Hit the like button if this investigation into what will really happen on December 19th has given you information and perspective you didn't have before. That simple action tells the platform that this content matters, that people value in-depth exploration of astronomical events beyond surface-level headlines. And drop a comment telling me where you're watching from. I want to see how global this audience is, how many different locations are represented among people who care about interstellar visitors and rare cosmic encounters. Your comment becomes part of the record of this event, documentation that people around the world were paying attention when 3i Atlas made its closest approach to Earth. Subscribe to this channel if you want to be part of future investigations into cosmic events that challenge our understanding and expand our awareness of the universe. There will be more interstellar visitors. There will be more moments when the cosmos offers us opportunities to witness something rare and meaningful. Being subscribed ensures you'll know about these opportunities when they arise, that you'll be part of the informed community that notices and appreciates these cosmic encounters rather than letting them pass unrecognized. December 19th is coming. The countdown continues. 3i Atlas moves closer to Earth each day, following the trajectory that has been calculated with precision, approaching the date of closest encounter that represents our best opportunity to study this interstellar visitor before it fades from view and continues its journey outward through the solar system and back into the interstellar medium from which it came. This is our moment to observe, to learn, to connect with something that originated beyond our solar system and travelled through the darkness between stars to pass briefly through our cosmic neighbourhood. This is our chance to be witnesses to the larger reality of a galaxy where material moves between stellar systems, where our sun's gravitational influence creates a kind of net that occasionally captures samples from other regions of space, allowing us to study material that formed light years away. The comet doesn't need us to notice its passage. It will follow its path regardless of human attention. But we need moments like this, opportunities to lift our perspective beyond immediate concerns and connect with the universe we're part of. We need reminders that our planet exists in a dynamic cosmic environment, where events of genuine significance occur on timescales we can witness. We need chances to participate, even as observers, in the ongoing story of discovery and exploration that defines humanity's relationship with the cosmos. December 19th offers exactly that opportunity, wrapped in the story of a single comet making a single passage through the inner solar system, a passage that will never repeat but that reveals truths about the nature of the galaxy that persist long after this particular visitor has departed. Notice it, mark it, remember it, and let this moment of cosmic connection remind you that you're part of something vast, something ancient, something that extends far beyond the boundaries of our planet or even our solar system, into the larger galaxy where countless stars shine and countless worlds orbit, and material moves between systems carrying information about the diversity of conditions under which planets and comets, and possibly even life, can form. That's what December 19th means. That's what 3i Atlas represents. That's why this moment matters. And that's why, despite all the competing claims on your attention, this is worth noticing, worth understanding, and worth remembering as the date when humanity witnessed an interstellar visitor at closer range than any confirmed interstellar comet has approached our planet in recorded history, a moment of genuine cosmic significance that you were alive to experience.